Welcome everybody to this webinar on our new version 11 of the Gurobi optimizer. So here's the agenda of today's presentation. So we are going to talk about the LP improvements that we made in the new version, about the mixed integer programming improvements. Then we talk about the most prominent new big feature in Gurobi 11, which is the ability to solve mixed integer nonlinear programs to global optimality. Then we have a few additional nice features to talk about, and then a few words about news in our APIs, in particular Java and Gurobi Pi. Then I'm talking and presenting a bit about another nice new feature, which is the dynamically distributed tuning tool. And then I hand over to Fernando, who is presenting you the news in the cluster manager and compute servers. Okay, let's get started with the linear programming piece of Gurobi 11. So here is the summary slide of all of the speedups that we got compared to the previous version 10. So as you can see, in our default linear programming settings, the speedup was not that big this time, but we did achieve some nice speedups on the barrier solver and also on the primal simplex algorithm. In that table, you see a very big improvement on second order cone programs. And while we did actually really improve the performance there, this number is a little bit too high, I would say, in practice, because this is a large part of that is due to fixing some performance bug that we had in the code. So not anything that is about correctness, just that we had a big kind of bad loop that is behaving badly in terms of performance when very dense cones had been involved. So this has been fixed, but still performance is pretty good here. Looking at the linear programming performance from a historical perspective, you see here that since version 1.1, with the default settings, which had been dual simplex for versions 1 to 4, and concurrent LP since version 5, we have now in total achieved a speed up in that particular metric that we are using here of more than 45, which is pretty nice. But you see also that the performance improvement from version 10 to 11 was not that big, but we have seen similar situations previously, say from version 7 to 8, and in particular also from 8 to 9. And then again, we had a nice jump in version 10. So it doesn't mean that we are running out of steam here. It just means that this time it wasn't that good, the default performance improvement on LP. Okay, some features for LP. So we have two of them that I want to discuss. One is the solution target parameter. So this is a parameter that was actually already introduced in Gurobi 10, but only as an undocumented parameter. And now we are supporting it as a documented parameter that is implemented in all of the APIs. And this has the following meaning. So if you just leave it at its automatic value, then there's no change for you. It is then just equal to its value 0, which just means you want to find an optimal basic solution by default. But you can also set that parameter to 1, and that means you are actually not interested in a basic solution. What you really only want is a pair of optimal primal and dual solution vectors. For example, when the solver then decides to use barrier or decides to use concurrent LP, also including barrier, then the crossover step is not needed because you don't need a basic solution. And also unfolding after symmetry reduction is no longer needed. And additionally, we can do some additional pre-solve reductions that would otherwise be incompatible with the basis statuses of the variables and constraints. So if you only need an optimal solution but don't care about basic, then that's the parameter to use. And we have not only made that parameter public, we also have improved the performance of that particular mode. So while in Gurobi 10, you could just have set this undocumented parameter to 1, which was then but basically just equivalent to setting the method to using barrier and disabling crossover. Now with Gurobi 11, the algorithm is a little different. So we would also often run the concurrent LP with barrier included without crossover, but then also primal and dual simplex. And the question is only whether we want to run concurrent or not, or just fewer barrier. And this is now decided by employing a gradient boosted tree. So this is a machine learning algorithm that we have trained with our problem data so that it will automatically decide whether to use pure barrier or concurrent LP. And overall, all of the improvements and this particular machine learning decision here gives you a 23% overall performance improvement as compared to Gurobi 10 with solution target 1, and 46% performance improvement on the harder models for which at least one of the two versions takes at least 100 seconds. Good, then the other parameter that I want to mention is the concurrent method parameter. So in Gurobi 10, there was only the method parameter that everybody knows, which is where you select whether you want to use primal or dual simplex or barrier, or a non-deterministic concurrent LP or a deterministic concurrent LP. And then at some version, we also introduced another value 5. For this very specific case, you want to have deterministic concurrent simplex. So just primal and dual running in two parallel threads. And then, of course, the question is, can I have also non-deterministic concurrent simplex? That was one reason to introduce another parameter, because we now want to make it a little bit more systematic here by kind of removing that fifth value again, so that you can only now decide between non-deterministic and deterministic concurrent LP. But if you decide for one of the two versions of the concurrent LP, then you have the second parameter, concurrent method, where you can actually specify which of the algorithms you really want to run. So that means the old value 5 is equivalent to specifying deterministic concurrent LP, so setting method to 4, and then selecting a value 3 for the concurrent method to say you only want to have dual and primal simplex. So you could have already achieved the very same thing by using the specific concurrent environments that you can then use to specify your own parameter settings as you want. But doing this with this concurrent method parameter has the advantage that you can then still benefit from the enhancements in Gurobi 10, where the pre-solve is doing in a joint fashion for all of them together, and then only then we split up in the individual threads for the concurrent methods, which is not the case when you are using the concurrent environments. Okay, let's move on to mixed integer programming. So here the performance comparison to the previous version is pretty solid. So for mixed integer linear programs, we have achieved a 12.4% speed up on the harder models. For mixed integer programs with a quadratic objective function, so MIQPs, it's even 22.8%. And for models that have quadratic constraints, and everything here in this table is convex still, that would be 18.2%. So pretty nice improvements again. So when we only look at the MIP performance evolution here, we see that since version 1, Gurobi has achieved an 80 times speed up now with the version 11, which we think is pretty impressive in that metric here that we are using. Good, so where does the performance improvements come from in MIP? So I won't go into those details here. The message is just that, as usual, which is basically happening at every single release, the improvement in the MIP performance comes from a large set of small improvements of individual components. So again, we have improved stuff in pre-solve, in the node pre-solve, in the branching variable selection, in cutting planes, and in how we use and detect symmetry, and then also some other improvements. So for example, we have just improved our sorting methods, and that led to an overall improvement of 0.4% on the algorithms. One particular thing that I just want to pick out here and talk about a little bit is the new cutting planes that we are including, the mixing path cuts. Those cuts have been developed by Oktay Günlük and Yves Pochet in 2001 in that paper that is listed here in Math Programming. And then Philipp Christoffel in his PhD thesis has done a very nice implementation of that algorithm, and the implementation in Gurobi is basically following what Philipp Christoffel did and what he was calling the so-called U-cut procedure. So we are just using our regular MIR aggregation procedure from which we would also separate MIR cuts, flow cover cuts, knapsack cuts, and so forth. And then now, as another step, we also look at mixing path cuts on such aggregations. So as always, with the cut parameters, you can set them to -1 meaning automatic, 0 meaning off, 1 meaning just at the root node, and 2 meaning also at the local nodes of the search tree, and in a more aggressive fashion. And the performance impact from these cuts is that the speedup is about 1.2% on the harder models, which is pretty okay for just another cutting plane separation method. Good, let's move on to the more bulky topic of this presentation and the big feature of Gurobi 11 in terms of the algorithmic improvements. So this is nonlinear programming. So first take a look at the very related problem class, which is the non-convex quadratic programming. Here we have achieved another really nice speed up in version 11, and the speed ups of version 9.1, 9.5, and 10.0 were already very significant compared to version 9.0. And so since the start, when we introduced that feature in 9.0, we now have achieved an 86 times speed up or so. So this is really, really cool to see that we are still able to make such big improvements on that front here. Comparing the performance to the previous version 10, on the harder models, this non-convex MIQCP is now 5.8 times faster than version 10. One thing I'd like to point out, this is now still for the quadratic case relevant, is that we have changed the meaning of the automatic value of the non-convex parameter. Because now with version 11, we feel that that solving non-convex quadratic programs is kind of now something that we can regularly do often without big problems. Of course, this is always a challenge, but many problems we can just solve. And so we decided that it is time to change the automatic value. If we encounter a non-convexity in your model, Gurobi by default settings will now just solve it and give you an optimal solution. If you want to have your previous behavior back, so that means, for example, you think that the problem should be convex, and a non-convexity is more a sign of an issue in your problem formulation or an issue in your data, and you want to be informed by that, then you set the parameter to 0 or 1. And then again, you will get this Gurobi error when a non-convexity survives in pre-solve. So that means this can change, this change can break your code if you're relying on that error. So then please set non-convex parameter to 1 if you need that. Good, and now getting into the non-linear world here. So Gurobi 9.0 already supported the stating nonlinear constraints through its API with these functions here that you see on the right-hand side and on the left-hand side, the corresponding mathematical terms. One is now missing because this has been introduced later in Gurobi 9.5, I think, or 10, which is the logistic constraint that is also in the list. But the point is, in Gurobi 9 and Gurobi 10, you could specify these constraints, but you were not able to solve them as a nonlinear program. Gurobi would only translate these constraints into an approximation of the model using a piecewise linear approximation. Of course, you could set the parameters such that the pieces become very small and the approximation is then very good, but still it's not the exact problem that Gurobi is going to solve. With Gurobi 11, you can choose to treat those nonlinear constraints exactly. And we would do so internally by a dynamic outer approximation that I want to discuss now. So how do you specify that you want that new behavior? There are attributes for the so-called general function constraints, and a parameter to control that. So as with all of the attributes for these function constraints, it's always like, if you leave the attributes at their default value, then the parameter decides what is going to happen for those constraints. So that means in particular with the attributes, you can now, for each constraint individually, select that this constraint should be treated as a piecewise linear approximation, the other constraint should be treated exactly using a dynamic outer approximation, and so forth. But usually you would just leave all of the attributes at their default value -1, and then just flip the single parameter func nonlinear to its value 1 to say I want everything treated as dynamic outer approximation to get a fully correct, precise result. Okay, so how is this dynamic outer approximation being implemented? So you see here now the comparison on the left-hand side. So this is now some nonlinear function that you see on the left-hand side. This is what you would get if you use the old static piecewise linear approximation. So the red line is here now your feasible space. And of course, you can see that it could be that that Gurobi will find one point on that red line and says this is an optimal solution, for example. And it would, of course, often not be exactly on the blue line that you have specified through the API. This is the nature of an approximation, right? On the right-hand side, this is how Gurobi would behave if you set this func nonlinear parameter to 1. It would construct an outer envelope around your function and solve this relaxation. And of course, it would mean that the relaxation solution could violate your function. That's true. That's of course clear. And then by branching, we would refine this approximation until it is so small that the difference between the relaxation value and the true nonlinear function constraint is small enough that we can say this is kind of feasible. And so you see here when the bounds get tightened, then on the right-hand side you see how the envelope gets smaller and the feasible region for the relaxation gets closer to the actual feasible region of the nonlinear constraint. So, and this relaxation, there are a few tricks how to construct this outer envelopes. And I'd like to start with a simple case. Here is a logarithm function, and this is concave across the whole domain of the logarithm function, which is, of course, the positive piece of the x-axis. So it is concave, so which means that the lower envelope is always just given by a single linear constraint, namely the secant that goes through the lower and upper bounds of your domain. And the upper envelope is given by an arbitrary number of tangents, which are globally valid. So we can just put as many tangents as we want, and the more we put, the closer we get to the curve of the logarithm function. In this example, we just use 2 of them, and then you have here this envelope and the corresponding feasible region for the relaxation, and that's it. Now, what happens if the function is a bit more complex? So say we have the sine function, but let's assume now the global bounds of the variable are still such that everything only happens in this case, a convex region of the sine function. Then we can do the very same trick, right? The upper envelope is just given by the secant, and then now the lower envelope, because it's not convex, is given by these tangents that we can again construct, and then again that's it. And a similar story if we are fully in the concave part of the sine function. So, but now what happens if the domain spans more than just the concave or just the convex part of the function? Then we have to be a bit more clever. So what we are doing here now is we are, for the lower envelope, computing the leftmost solution x0 that satisfies this equation here. And so what is the geometry behind that equation? It means that we want to find a tangent to the right of this curve here, such that the tangent is as tight as possible for the left part. So this tangent that you see here is not tight enough. So this is not what we are looking for, because it's very loose, right? On the other hand, this tangent here, this is too tight. It cuts off parts of the feasible region in the top left region of the function. So what we are looking for is this tangent. And this tangent is just the solution of that equation that you see here, that the slope of the tangent should be in such a way that it hits exactly the lower bound of the function constraint there. And this can be calculated by a few Newton iterations relatively easily. So the remaining part right off that point is just convex. So here we do the same thing, just produce some tangents. And then for the upper envelope, we do the very same thing. We find the rightmost solution to that equation here so that it goes exactly through the upper bound there, and then we do the tangents on the left-hand side of that point. And that's it. So now, if it's even more challenging, the problem, so like we have the domain of this, in that case, again, the example, the sine function is even larger. Yeah, then in the middle where we have all these maximum and minimum values of the sine function, we can't do anything than just putting in the boring box constraints here with the y variable between -1 and 1. Only on the leftmost and rightmost piece of the function we can perform again these tricks that I just showed you to make the envelope a little bit tighter than just the box around the domains. Okay, and then now when we have all these envelopes and have with that the linear programming realization, we now have to define how we search for a feasible and then also globally optimal solution. And that is very similar to MILP branch and bound, and actually pretty much identical to the algorithm for the non-convex quadratic programming. Namely, the important pieces here or differences to the MILP case is that a feasible solution can be identified by, as usual, making sure that the integer variables have an integral LP value. But then in addition, we also have to check whether the nonlinear constraints are satisfied. Of course, the linear constraints will be satisfied automatically because we are solving an LP relaxation, but the nonlinear constraints may be violated because we are only having a relaxation of these nonlinear constraints in the LP. And so that in particular also means if that is not the case, then we may need to branch on continuous variables. And that is a little bit of a challenge because it implies two additional things, namely that on the one hand side, the infeasibility of this LP relaxation may not be directly resolved in the two child nodes. It could be that one child node is then still exists where this very same LP relaxation is still feasible. And moreover, the branching split point, so that particular value on which we branched on the continuous variable, this is now feasible in both child nodes. So as opposed to MILP, where the split into the two child nodes is really a partition of the search space. So, and how does the branching work? So this is really identical to non-convex MIQCPs, or very similar. So, and this is why I'm using this example with a quadratic function. So you have this point T here that is the solution of your LP relaxation. It is violating our non-convex constraint. So then we split on that variable, and by doing so in the local child nodes, we are going to refine our relaxation. And with this refinement, we will typically cut off this LP relaxation solution. But as I said previously, it could be that in one of the two child nodes, the LP relaxation solution is still feasible. So this is how we move forward. And then I'd like to point out one of the challenges with the current Gurobi 11.0 API that you have to face and that you have to keep in mind. The Gurobi 11.0 API only supports this set of specific univariate functions that we have implemented. So sine, cosine, exponent, logarithm, tangent, and so forth, but nothing else. But of course, you can build more complex functions out of these. But for those, you have to explicitly introduce auxiliary variables and auxiliary constraints to make it happen. So let's take that one here as an example. So we have that function f of x that should be equal to the square root of 1 plus x squared, and so forth. And this you cannot enter into the API directly. You have to split it into its components. So here you would, for example, introduce an auxiliary variable u that should be equal to 1 plus x squared. So this is just a non-convex quadratic constraint. This is fine. Then you introduce a variable v that is equal to the square root of u. This is again a non-convex quadratic constraint by saying u is equal to the square of v. And then you have this term here, which is just the sum of x and the already introduced auxiliary variable v. And then the logarithm of the W, this is then now this function constraint that we support, that Z should be the logarithm of W. And with that, the constraint just becomes V plus Z smaller or equal to 2. But of course, you have introduced this bunch of auxiliary constraints and variables. And this is how you have to do that. So this leads us to one or the main limitation of the Gurobi 11 approach that you need to be aware of. This procedure that you have to disaggregate that, so basically almost every solver for global nonlinear programming is doing that internally as well. But for Gurobi, you have to do it as a user explicitly. So we are not lacking any kind of algorithmic components here. It's just that you have to do that yourself. But it has one implication, namely the effect of the feasibility tolerances. So when you specify a problem in Gurobi, then of course the feasibility tolerance is applied to each individual constraint. And because you have to disaggregate the nonlinear constraints, that means the feasibility tolerance is applied to each individual piece in your disaggregation. And that could have a surprising effect, namely that then the overall composite function that you wanted to model might be more violated in total than the feasibility tolerance. So given an example here, we have that function y is equal to the x divided by sine of x, which is a very nice function. So everybody knows that even at point 0, where the denominator has a root, this function still behaves very nicely. But because of that root here of the denominator, when you disaggregate it, then you can get into numerical issues. And I show that here with an example. So take that solution that is very close to 0, so 10 to the minus 4. And then the corresponding y value would be that number that is shown here. And if you disaggregate it in that form, this is how you have to enter it into Gurobi. Then you introduce these additional auxiliary variables u and v. And the solution here is, this is the kind of almost exact solution up to rounding in the last digit, which is fine. So everything is feasible. But Gurobi could also give you this slightly modified solution, right? It could say, yeah, the x value is still 0.0001, fine. But then it could find a solution where the u variable is 10 to the minus 6 away from the true value of sine of x. Which is fine, right? Because that is within the feasibility tolerance of that sign constraint here. And then v and y should then again be the exact solutions of their corresponding nonlinear constraints. But as you can see in total, it means that the y variable, that is your actual structural problem variable, is 10 to the minus 2 away from its true value of that composite function evaluation. So this is how the error in the u here could translate into a larger error in y. And the reason is that we have introduced that auxiliary constraint with the denominator, and we are now operating in a very steep area of that reciprocal function, right? And this is where numerics can scale up. Numerical issues can scale up. So that means, on the other hand, if you are just operating with functions in regions where the slope is not very large, then you would probably not suffer from that limitation here. And but that brings us already to the roadmap, to the clearly canonical roadmap for Gurobi 12. We are going to add also API so that you can state composite nonlinear functions directly. This is then also not only more convenient for you, but with this way you can also tell Gurobi what your actual function is, and then Gurobi can make sure that the feasibility of this composite nonlinear function is satisfied. Moreover, of course, we are going to improve the global MINLP performance and robustness, and we are working on our interior point local NLP solver even more. So right now we have that already, but it's only used internally for primary heuristics. One thing that we could do in Gurobi 12 is to expose it so that as a user you can also call it directly from the API. And obviously, numerics are always challenging for mixed integer nonlinear programming. This is what we always need to work on. Okay, so let's talk about some additional nice new features. So the first one I'd like to mention after I'm talking about the new versions here that we support in terms of the software, so Python 3.12 and the newest MATLAB version, of course, are supported, is our ability to now copy models between environments. So the use case here is that you want to have the copy of your model in a different Gurobi environment, and then potentially modify that model a little bit in order to have two environments available so that you can run yourself two optimizations at the same time. Because the Gurobi environment is not thread safe, you cannot do that with just a single environment, so you have to have a second environment to do that. And now being able to copy a model from one environment to another makes that more convenient if you want to solve two related models on two different threads. One caveat I have to mention is that with compute server, it works. So if you have your model on your client environment, you can copy it into a different client environment and also into a remote environment, but you cannot copy a remote model into something else. That is not possible. Another small feature I'd like to mention is now the ability to interrupt a solve, change the number of threads, and then resume it. Of course, you could have interrupted a solve and resume it previously, but until Gurobi 10, when you change the threads parameter in between, then this change is basically ignored. Gurobi just continues with the number of threads that had been specified at the start of the solve. This has now changed, and one of the use cases is a memory limit. So you could say, I want to make sure that I'm only using 4 gigabytes of memory, so you would set the soft mem limit parameter to 4, but you want to start with 8 threads, say, or just with the default settings of the threads, because you typically want to have maximum performance, and for that reason you just want to also use multiple threads. But if you hit this memory limit, so if the status is mem limit that you receive, then you could say, okay, then let's set the thread parameter to 1, because just using a single thread is usually using much less memory, and then optimize and resume your optimization so that you stay within your memory limits. Good. Then some words on our APIs. So Java Gurobi Pi enhancements. So about Java, I'd like to mention that now the Gurobi Java package is available on Maven Central. So that should be a nice simplification for our Java users in their deployment processes. So Maven Central is basically the standard repository for Java packages, similar to what PyPI is for Python. But with this deployment of our Java package on Maven Central, we needed to also change the package name to the now default package naming scheme, which is for us would now be com.gurobi.gurobi. The old name was just Gurobi, so that means for you as a user, you have to change your import statement. So instead of import Gurobi, you would say import com.gurobi. For Gurobi Pi, also a few changes that ease the installation. So on the one hand side, the type hints are not anymore needed explicitly. So the Gurobi Pi stubs package is gone. Everything is now included in Gurobi Pi. Then setup.py install does not exist anymore. So you should just use pip and pip install, and recall that with pip you can also do offline installations from the pip package, so that should be no issue. And then the conda and pip installation play nicely together, so that each of them then recognizes that the package has already been installed in the other system and so forth. So some improvements to the Gurobi Pi. So the matrix-friendly API integration is now also being done for callbacks. So that means, for example, if you have lazy constraints, you can use the matrix-friendly API objects to state these lazy constraints. Moreover, there is improvements in how NumPy style concatenation works. So this is now just working. And you can also vectorize indicator constraints and broadcast them. So the last line here that you see here with the single variable z and this whole linear set of linear equations using the add operator, it just means that the same binary variable should trigger all of these linear constraints that are represented by the matrix vector system. Some other notable mentions here. So callbacks can now be, any callable object can now be used as a callback. So this avoids this workaround where you would have to put your own data somehow into the Gurobi model such that in the callback you can read the data again. Now you can just use your own object as a callback for Gurobi where you already have all your data. And then performance improvements, those are, we have implemented some performance improvements ourselves, but most of them come from just using the newest Python version for compiling our Gurobi API. And this makes the term-based modeling something like 10 to 20% faster. And there are also cases where it's actually 2 times faster for sparse data. So finally, I like to mention our new dynamically distributed tuning feature. So this is a nice thing that we have added in Gurobi 11, where you can then better use your cluster for your tuning. But let's recall what tuning actually is. So with a tuning tool, you can automatically find good Gurobi parameter settings in order to solve a model, but typically a set of models faster than with the default setting. So the tuning tool would explore the parameter space and try a large number of combinations and then tell you what is a good set of parameters. So, and there are 3 ways of doing that. And this is already the case in Gurobi 10 and earlier versions. So of course you can just do it locally on your laptop or desktop computer, let the tuning tool just run for a weekend or so and then spit out good parameter settings. You can also do that in the compute server environment, so connect with your client machine to the compute server, let the compute server do the tuning, and you can even use distributed tuning, which means you have your connection to the compute server, but the compute server is accompanied by a pool of what we call workers, and they all share the load of the tuning process. And the tuning behaves very nicely in that regard because the speed up from adding additional workers is almost linear because it is so easy to, so each parameter configuration and problem instance that you need to solve is an independent optimization job that can easily be scheduled on some worker in parallel. And now with Gurobi 11, we have improved that distributed tuning in the sense that now it is very easy for multiple users to use the same cluster and all the resources are shared nicely. So if one user comes in the morning and starts that tuning job, they will just get the whole cluster with all of the workers working on that tuning job. And then if the second person comes in and also wants to do some tuning or even some other regular compute server calculations, then some of the workers will then be handed to that second person automatically, and we have a nice automated load balancing scheme for that so that you can use your resources with very nice efficiency here. And with that, I'd like to pass over to Fernando, who is going to tell you the latest news about Cluster Manager and compute server enhancement. So Fernando, please.
Yeah, hello everyone. So I would like to share with you the Cluster Manager and compute server enhancements for V11. So as you know, the compute server with Cluster Manager facilitates the development and use of optimization services on premises or on private cloud with features like user management, cluster monitoring, optimization job monitoring. Now with V11, we have improved the look and feel, the user experience, and the security. So you will have a completely revamped UI with new features, but also we have improved in the web request security headers. With this, we were able, or we obtained a grade 8 from securityheaders.com. Next slide, please. In the UX side, for the user experience, we have a new feature, which is the time zone selection and formatting. Now, from the user menu, you will be able to select which time zone you want to display in your data, either UTC or your local time zone. And this will be reflected across the whole cluster manager. The time zone that you have selected will be indicated in the column headers and the property tabs. Next slide, please. But also now, in addition to LDAP, V11 adds support for SAML2 user directories. With this new integration, you will be able to use any identity provider that supports SAML, like Azure Active Directory, Okta, Google Workspace, or John Cloud, among others. You will be able to use them as a way to authenticate your users in Cluster Manager. Next slide, please. So with this, we also have a new dedicated sysadmin login page. This was created in such a way that a sysadmin user can still be able to log in locally, so that access can be managed even in case of a problem with SAML 2.0 configuration. That means that if for some reason you configure something wrong, your certificates are not correct, you are going to be still be able to log in as a sysadmin and fix those possible issues. Next slide, please. And with that, in SAML2, for Cluster Manager, you will find a new settings in the authentication section, where you are going to be able to configure this authentication provider. And with that, we are providing some special options for SAML2. The first of them is that you will be able to import the identity provider XML metadata for any identity provider that can generate these XML files, which is most of them. You will be able also to import certificates to verify the authentication response from your identity provider. We also support both request bindings, post and redirect, so you can also select that depending on what your identity provider supports. You can also select a custom mapping of user attributes like name, email, username, last name. Also, and not included, well, it's not only for SAML2, we have a new case sensitivity setting. This setting will help you to decide if you want to disable the case sensitivity validation when you are logged into the cluster manager. This one applies to the regular authentication, LDAP, and of course, SAML. Also, when you have decided your service provider configuration live mappings, you will be able to download this XML data and import it in your identity provider. Next slide. With SAML, we also have a new authorization flow. This authorization flow will be used when you want to log in with GRB cluster for a specific username. So once you try to log in and you have SAML2 configured, this will generate a device ID. So this device ID has to be authorized in a web browser, which can be in the same machine or in any other machine. So after you try to log in, a new web browser will be tried to be open in the computer. If that's not the case, you can follow the link. And then within the web browser, you will follow the SAML2 authentication flow, and then you can authorize this device. After doing that, the GRB cluster will authenticate, and you can proceed and work as usual with the authorization completed. Next slide. Okay, that was for SAML2, but also we have improved in database support. We already have existing database support for Mongo and Amazon DocumentDB, which we have been keeping testing for newer versions. But we also have now a new support of Cosmos DB 4.2 on Microsoft Azure. You just need to make sure that you are starting Cosmos DB 4.2, and with that, you're going to be able to deploy your cluster manager using Cosmos DB. Next slide, please. And finally, we have better server-side limits. These server-side limits can be enforced by IT as a policy, which means that you can configure these limits in the configuration file of your node, and the clients cannot override these limits. The first of them is the mem limit, which will limit the total amount of memory. If more of this memory is limited, Gurobi will fail with an out-of-memory error. If you got this out-of-memory error, it's not possible to retrieve a solution information, and it will just fail with this error. But then we have soft mem limit. This one also limits the total amount of memory available to Gurobi, but if more of this memory is needed, Gurobi will terminate with a mem limit status code, leading to a graceful exit of the optimization such that it is possible to retrieve solution information afterwards. Or in the case of an MIP solve, you can resume the optimization. And finally, for the time limit, this one limits the total time extended during optimization. If this time limit is reached, the optimization will return the time limit status. And that's it. Thank you.